now go by and try to solve whatever we had spoken about this surface integral. Just note that I am expecting that you to know what is I vector, j vector and k vector. Look up any book on vector analysis for this or the book of calculus that we have prescribed. This is our last class. So, we have to do things quite fast. So, I will explain one or two points and then go on doing the rest. So, here we start with the first surface which is exactly facing us, the one here, where we are essentially bothered about you observe there is no change in the vectors x, but the change is essentially in the vectors y and z. So, your x remains to be equal to 2 in the first case. This is the first surface, this is the surface 1, the one this is the surface 1, right. Then d of a, this vector is dy dz along the I vector. So, v dot dA, assuming that x is equal to 2, so rest is 0. So, x is equal to 2, keeping that in mind. So, my v dot dA would become 2 x z dy dz. Of course, you can ask what about here we are doing a dot product. So, you are taking whatever coefficient have with I and whatever coefficient we have in v with I, and then we are multiplying them. Now, x is anyway 2, so it will become 4 z dy dz. So, in this case v dot dA, we are basically having a double integral. So, 4 z dy dz, which we can of course write dz dy by phi Bini. And it will ultimately come out to be 16 in this case. Similarly, we will go to the next one, just the opposite one to 1, which is this the outer one, this one, we will call it the second one. So, there you can observe that x is equal to 0, right, and dA vector is dy by dy into dz, but the direction is not in the direction of the I vector, but the direction is opposite to the I vector. So, there would be a minus sign. So, again v dot dA is equal to the same thing 2 x z dy dz, but here because it is 0, this is 0 because x is 0. So, integral v dot dA, this part on this particular part of the surface is 0. So, similarly you will go on doing the other case. Now, you take the case say y equal to 2, then here you will have y is equal to 2 and you will have dA vector is dx dz vector along the j vector, and then v dot dA would be equal to x plus 2 dx dz, and then you just if you integrate in the same way using double integrals, and then your answer is 12. So, this is nothing but 0 to 2, 0 to 2 x plus 2 dx dz, and that is 12. So, you can go on doing it for all the other surfaces and then add up. If you want to check the answer here is 20. So, this example is from the book called Electrodynamics, Introduction to Electrodynamics rather, yeah, Introduction to Electrodynamics. I purposefully I took it from physics books because that gives you much better fast introduction to the thing, Introduction to Electrodynamics. It is a famous book by David J. Griffiths. It is a very, very famous book. Okay. So, once we are through with this, let us go and see in the board. I took another example from Griffiths to explain to you how things can occur for volume integrals. What is a volume integrals? In volume integrals, we are only taking volume integrals for scalar functions. We do not usually talk about volume integrals for vector functions, but then you can do, then you have to separately work on the scalar parts. So, here is a function of x, y, z, and d tau is the volume element. So, if there is a volume like this, a body, then d tau is a volume element which is nothing but dx into dy into dz. So, this is the volume element whose volume dv or d tau is nothing but dx into dy into dz, elemental volume. You can understand this is. So, if you move along this direction, the x direction, it is dx, if you move along the y direction, it is dy, if you move along the z direction, it is dz. So, you draw a small cube, basically you break the body up into small cubes and find the volume of all those cubes, and then multiply those volumes with the functions, add them up, and then take the limit by making the volume smaller and smaller, and that is exactly what is going to give you the volume integral. This is the last part I said for mathematicians, the people who are actually doing some math or interested. Say I am going to take this one over this prism. So, there is a prism which is cutting, which has vertices at 0, 3, 0, 0, 3, 1, 0, 0, 0, 1, 0 coordinates and the point 0, 0, 0, the origin. Now, you see here the line joining 1, 1, 0 and 0, 0, 1 is actually the line in 2 dimensions, which is given by the equation x plus y equal to 1. This line is nothing but x plus y equal to 1. So, when y is varying from 0 to 1, my x is varying from 0 to 1 minus y. So, if I want to integrate, so I will first integrate with x varying from 0 to 1 minus y, and then I will integrate from y varying from 0 to 1, then z varying from 0 to 3, and by doing this I get the answer 3 by 8. So, I hope this is all pretty clear to you. If you are not so clear, just look at the diagram once again. See that this is x plus y equal to 1 and this is, so I am first varying x, but when I am varying x I am varying y. So, what I am doing, when I am varying z from 0 to 3, y has to then vary from 0 to 1. When I am varying y from 0 to 1, I am varying, while I am varying z from 0 to 3, y gets varied from 0 to 1, but while I am varying y from 0 to 1, x is getting varied from 0 point, x is getting varied to this point 1 minus y. So, this has to be, this sort of thing has to be very carefully done, and that would finally give you the integral. See, what you are essentially doing by trying to find some sort of a volume, you are essentially trying to do what? You are trying to basically get this area out and then multiplying by the height, that is all. Now, I come to some important theorems here. I will first mention the Gauss divergence theorem, which relates the volume integral and a surface integral. It tells you that if you are trying to compute the volume of, you are trying to compute the volume of the divergence of a vector, and then if S is the, so this is the volume, so this is of the volume, this is the volume of an object, these are 3-dimensional objects, say like this. So, let us make it 3-dimensional. So, basically now I am taking the volume integral of a vector, the divergence of a vector over this. So, how it is moving out from the volume. So, maybe, so that how say a fluid is moving out from a given source, or light is moving out from a given source. But if I want to compute the volume integral, I can also convert it into a surface integral. If I consider the surface of this body, the same body whose volume I am considering, if I consider the surface, then if I take the surface integral over the whole surface, so I have put this circulation sign, surface integral then that is same as the volume. So, basically what it is trying to say that the spreading out of say a fluid from a given point is same as its flux across the surface area. This is the flux, it is the change of volume per unit area. The change of volume per unit area is given by the flux. So, and then over the small elemental volume it is V into dA. So, per unit area this is the volume per unit area and the change of this is the change of the volume per unit area. So, amount of fluid the amount of fluid that crosses a unit area in a given unit time, that is the flux, and this is done over each small elemental area. So, what the total is this is given by the surface integral. So, it tells you that the total flux gives you the total divergence out of the volume, the amount of fluid which moves out of the volume is same as the total flux over the region, which is physically the case of course. Then there is the Stokes theorem. What does the Stokes theorem do? It tells you that if you want to take the surface integral of the curl of a given vector V, then if you take the perimeter of the same surface, the perimeter of the patch of this surface, this sort of surface, if you take the perimeter of that surface, of that patch, surface patch, I cannot talk about a closed surface, then it will be difficult. So, of course, you can then define a perimeter of the circumference sort of thing. If you have a sphere, you take the circumference. So, if you have surface area basically. So, basically if you take the surface integral over this patch, a small patch of area like this, then Stokes theorem says it is same as taking a line integral over the perimeter line, the boundary, line integral over this whole closed boundary. That is what the Stokes theorem says, but it is not so easy to immediately realize and understand these two results. It is very short time to really speak about them. Then there is the Green's integral, which is essentially a two dimensional thing, which says that if you have a vector function which is given in terms of mi vector plus nj vector in terms of two vector functions, which are themselves as function can be written as functions of x y, then if I move along, so I have this circular closed curve which is enclosing the region R, and if I move counterclockwise, moving counterclockwise means if I move along the curve, the inner part or the region of the curve should always be on my right. So, if I move along this, it will be always on my right hand. So, if I am moving along this part in counterclockwise fashion, then integral of m dx plus n dy is same as integral of del n del x minus del m del y into dx dy. If you are worried how this thing has come, this is nothing but the curl, or sorry, this is nothing but this vector in inner product with k vector. So, this quantity is this. So, their deep physical reasons are not so easy to figure out immediately, but what we are going to do is try to show you something of how to compute, because you have just seen how to compute surface integral. You can just check out the Gauss divergence. I will just give you a problem which can be of use to check out the Gauss divergence theorem, which is of great significance in many things. So, for example, you take a vector V. So, I am giving the example from Griffith again, which has lovely examples. So, you do it over the unit cube, means now you have a take the my region, the volume. So, now I have a unit cube of length breadth height 1 centimeter, 1 meter, whatever you want, 1 1 1. So, what is in this case? So, this will turn out to become, if you take the full divergence, it will turn out to become 2 x plus y. So, let us see how. So, basically you take the del, instead of going in too much detail for lost, you take the derivative with respect to x here, first case it is 0, plus derivative with respect to y. So, it is 2 x, here it is derivative with respect to z. So, it is 2 y, so it is 2 x plus y, that is the answer. Now, you take the volume integral. So, this is my required volume basically V. So, if you take the volume integral, that is nothing but 0 to 1, 0 to 1, 0 to 1, 2 x plus y dx dy dz. So, if you just compute out, so first you compute out 0 1, 0 1, 2 into 0 1 x plus y dx. So, it will be 0 1, 0 1, 2 into, you know what this will come out to be. This will become x square by 2 plus y x, that is from 0 to 1 dy dz. So, if we just do it 0 1 0 1. So, x square by 2 is, this will be give me this will give me half, 2 into half plus y. So, if you just go on doing this, your final answer would be 2. Now, surface integral, you know, here I am expecting over the whole surface. So, total surface, I am looking at total circulation. So, I am expecting over this one, over this one, the outer one, this one, the above one, and also the one below, just like the one we had discussed earlier. So, here we had not taken the one, we have just kept 5 surfaces just for heck of it. Here we will take, here we are taking, here we have taken the 5 surfaces, here we are going to take all the surfaces, even the last one. So, here you really have to make a check yourself and then show that this will be. So, let me take the first case where x is equal to 1, then and you have dy dz. So, the first case. So, this first this one. So, in this case v dot dA would be equal to 0 1 0 1 y square dy dz. Similarly, if you take the same thing on the other side, that is this one, the last, just the side, the one opposite to the first side, the facing side. Here you will have a minus sign and as before. So, in that way we will continue to do it and you verify that these are equal. So, hence we have finished the course. The last part had to be hurried, though we had tried to give as much example as is possible. It is not possible to do justice to multiple integrals in just 3 lectures of 20 minutes each, though I have tried to exceed in some of the cases, but I hope you have enjoyed the course. I tried to learn how to teach a very compact course in very short time. I learnt a lot in the sense that I now know what to do, what not to do, how to put things in order. This is actually a first experiment for me also, hoping that I will do better if I get a next chance. So, if there are any questions, please feel free to write on the forum and my TAs would get back to you. If they can't, I will definitely answer back to you. Thank you very much and hope you have enjoyed the course, and thank you once again for listening to me with all your concentration. Thank you.